Okay, so this was the part that we imported. So again, we got the two heaters on the bottom and a heatsink on the top, with a couple of these fins up here. So again, the objective is this thing is supposed to be a volumetric heat generator. So this is supposed to be an aluminum nitride heater with volumetric heat generation such that it produces 20 watts of total heat. And then similarly down here, this is the same thing, but it produces 35 watts of heat. So it's sort of an unevenly heated part. You can get some basic information about the geometry you just loaded in here. Sometimes it's actually useful to figure out what the bounding box is, so like what the coordinate of the front faces and stuff are. But in this case, we don't really need that. So once you have a part in here, you need to tell SimScale what it is that you intend to do with this part. So by the way, in this part, I actually have 3 bodies. So let me highlight this. So body 3, I forgot to actually name these parts. So body 3 is actually the solid metal heat sink. Body 2 is the back heater, and body 3 is the front heater. So there's actually 3 separate solid bodies in this problem that'll have to be coupled at their interfaces between them. And SimScale will usually automatically detect that. Okay, so when you're ready, click plus on the simulation. So you see these little plus signs on the left-hand tool thing. So if you click plus on one of those, it'll bring up a bunch of different possible simulations that you can do in SimScale. And we're definitely not going to go into all these in the class, but there are things like convective heat transfer problems. That's for like if you want to simulate only the fluid part of the flow going past a solid. There's conjugate heat transfer, which means you want to simultaneously simulate both the fluid and the solid. So in that case, it's actually doing a combination of finite volume method and finite element method. And they have 2 different variants of that have some different features that I'm not going to go into in this video. And then, so everything that says flow up here, all these flow things are basically doing finite volume method, except for this one up here, which is doing the lattice-Boltzmann method. Underneath that, you'll see things that say structural. That's the code word for finite element method. All of these techniques down here are doing the finite element method. So in particular, the heat transfer simulation or the heat transfer analysis does finite element method only on a solid. It's basically solving the Laplace equation subject to maybe some internal heating and boundary conditions and stuff. For the internal solid, you can take that a step up by doing a thermomechanical analysis where it simultaneously gets the heat transfer solution and does a static solid mechanics analysis of how that affects it. So like what I'm really talking about here is thermal expansion, stresses due to thermal expansion. So you can do a simultaneous heat transfer and solid mechanics simulation using the thermomechanical simulation. And then if you're doing just a like finite element method for solid mechanics, there's a static analysis up here. So I'm going to select since this is meant to be a finite element demonstration, I'm going to select the heat transfer analysis type, and that's going to basically load in the equations that we'll be solving, meaning the either the Laplace equation for a steady state or the diffusion equation with a transient thing if you're not doing steady state. So the very first thing at the top here on the toolbar is this heat transfer. When you are doing a simulation in SimScale, best practice is to basically just look over at the left-hand toolbar and march your way down. So, start up at the top. So the very first thing it did was it loaded in a simulation type. But even within that, there are sub-features, right? So you can do a heat transfer analysis type that's either transient, or meaning time-dependent, or steady state. In this case, I'm interested in sort of the steady state behavior of this heat sink, so I'm going to do that. You also have the choice, there's a little click button here for nonlinear analysis. If you load the nonlinear analysis, that allows you to, well, there's a description over here in the box. It's basically for situations where you have, for example, temperature dependent boundary conditions or material properties is the main thing in there. So I am not going to load that right now. If you want to, you can do that. But basically, it just allows you to specify some more complicated material properties. In this example, I'm just going to use constant material properties. All right, so it will already have loaded in the geometry as long as you had this geometry selected when you created the simulation. If it didn't, you can go back and select from a different geometry, but in this case, I only have one geometry loaded. It will usually automatically detect the bonds between different solids. So in this case, I had 3 solids, and it detected 2 interfaces between them. So there's one interface between this solid and this solid. So I believe that's bond 1. And then it detected another one between this surface and the surface on this solid. That would be bond 2. Sometimes it's a good idea to check out how it actually created that. So for example, what it's saying is that if those 2 solids touch each other to within 1 millimeter, which is actually not probably a good value here, then it's going to consider that part of the bond. I would say we should probably refine that a little bit because these solids, I mean, the size of them is only a couple millimeters thick. So I'm going to refine that by another order of magnitude and ask it to detect that again. But I don't think it'll have a problem identifying that interface. It already has basically, but just in case. So it will have detected these bonds. Element technology. So this is what type of finite element you want. So by default, I believe it just always uses tetrahedrons. You can, well, actually, I believe these analysis always use tetrahedrons no matter what, but you can actually choose either a first order, meaning a linear interpolation, or a second order, so a quadratic interpolation within the tetrahedron. In general, if you can get away with it, if it's not too computationally expensive, a second order element will get you a more accurate answer for fewer numbers of elements. So it's a good idea, as long as you're not running into computational limitations, to use a second order element if you can get away with it. The meshing takes about the same amount of time because they're all tetrahedrons. After that, you need to specify what materials all of these solids are made of. So when you go down to materials, you can add a material. So the materials let's say the top material for this is supposed to be stainless steel. They don't have stainless steel in the list, but you can just click on, let's say, steel, and then modify whatever properties it brings up. So let's say if this is stainless steel, the thermal conductivity would be closer to 15 watts per meter Kelvin, but the density would be fairly similar. You can do things like specify anisotropic materials. Here, if you selected nonlinear for the analysis, you can also specify the temperature dependence of the thermal conductivity. The specific heat will not matter in this problem because we're doing a steady state analysis where the specific heat doesn't matter. The other thing we need to do is assign a volume to that. So that means tell it what solid we're trying to simulate. So there's currently no volume assigned. Let me choose that solid. Oops. Right there. So if it didn't recognize when you clicked on the solid that you meant to assign it to that, after you have a solid selected, you can do the opposite. You can go over to the assign volumes thing on the left and select it. If you accidentally assign something you don't want to, you can either clear the list or you can press X to get rid of just the one body that you accidentally added. So I'll save that. And then I'll add some more materials. So I had meant to have aluminum nitride as the heater, the type of ceramic heater. That's not on here either, so I'll just fake make that. So I'll make a new material called aluminum nitride, which has a thermal conductivity of about, I don't know, let's say 200 watts per meter Kelvin. And I will assign both of these materials to that. So these two things are going to be made of aluminum nitride.